We are in section 7.2. We're going to look at a really neat application of the integral, which is when you have a function and its derivative that are, the derivative is proportional to the original function, then that lends itself very quickly to the what we call exponential growth and exponential decay. And so that is what we are going to work on in section 7.2. You'll find that we'll do a little bit of derivation to get the integration going, but after that we have the formula, and so we don't really have to integrate anymore. Okay, so I'm just actually going to start with an example and kind of motivate the integration first. Now, it tells you that in some chemical reactions, the rate at which the amount of a substance changes with time is proportional to the amount present. For the change of, and this is actually should be like a delta, but this computer program doesn't let me do Greek symbols. So for the change of D-gluconolactone into gluconic acid, for example, the rate of change is negative 0.6 times the original, whatever the original function was. And so it's proportional to the amount present. Okay, when T is measured in hours. So the question is, if there are 100 grams of D-gluconolactone present when T equals 0, how many grams will be left after the first hour? And so what this takes us to is this idea of exponential growth, and we can get there through integration to get back to y, just like we did on those couple examples that we just did here. So now I'm going to do this one time with this example, but once we have done it, you don't have to do it on each one. I mean, it would kind of be silly to do it on each one. So I'm just going to do it to sort of make sure that you've seen it, and in the textbook, he does it more generally, but we're going to do it with an example. So basically, we have here a differential equation, dy dt equals negative 0.6y. And our initial condition is they tell us if there are 100 grams of D-delta gluconolactone present when T equals 0. So our initial condition, y of 0 is equal to 100. So in order to get to y, what we'll need to do is go ahead and realize that we can integrate I'm going to play with this for a second. I'm going to take this equation dy dt, and I'm going to solve it for y. So if I divide both sides by negative 0.6, I get that, right? And then, I'm going to put the y over here, and I'm going to set that equal to the proportion. Okay? And then now, what I can do here is I can integrate both sides. So if I integrate this dy dt times 1 over y with respect to t, and I integrate this side with respect to t, then I will get that, notice that these dy dt's cancel, so you're just like 1 over y dy. That antiderivative is what? That's just ln y. So I get that the ln of y, and we have to put the absolute value, is equal to this antiderivative, which is just going to be...
Your conference is scheduled to end in 2 minutes.
T plus c. Okay? And then, what if I wanted to get to y? What would I need to do? I have what the ln of y is, how do I get to y? Mm-hmm. I call it you E it, right? Brandon, you still there?
Yes.
Yeah. I kind of lose you after that lady comes on. Oh, okay. Yeah. We can have it. Actually, the question was, do we not have to have a plus C on the other side? And the truth is, if you put a plus C somewhere, since you don't know what C is, it's just a constant, you can say, oh yeah, I moved it over and joined it up with that other C, and so they became big C. You know what I'm saying? So like the C is just a constant. So if he's here or he's there or he's in two places and then he joins up, it doesn't matter because he's just a number. Okay. All right. Now, if I E both sides, so if I do E to the ln absolute y equals E to the negative 0.6 t plus C, I get E to the ln y is just going to be the absolute value of y. And then this is just going to be E to the negative 0.6 t times E to the C, right? Because when you can kind of think of it that way. And to deal with that absolute value, what you can do is you can say, all right, this E
Your
to
conference is now over. Goodbye.
Goodbye. All right, this E to the C is really just some constant, right? And this absolute value is kind of telling you that it can either be positive or negative. It's on either side. So you can ditch that absolute value by saying plus or minus E to the C and then E to the negative 0.6 t. Okay? And the plus or minus E to the C is your constant when t equals 0. So it's your value when, or you can find that, this is just your number that you use, number that you find based on the initial condition. Okay, so what was our initial condition? Well, on our initial condition, we were told that there are 100 grams when t equals 0. And so for our problem, when t equals 0, if you plug 0 in here, e to the 0 is 1, you have to end up with 100. So you know it's going to be positive 100 is your E of C. Does that make sense? It depends on the problem, whether it's going to be exponential growth or decay, so whether it's going to be positive or negative, and they're probably going to give you some information to figure out what that initial condition is, or what that that's E to the C is. Okay, so because y at 0 equals 100, we see that E to the C is equal to 100, and here it's positive. So our equation is y equals 100 e to the negative 0.6 t. All right, and so now we can answer the question, which is how many grams will be left after the first hour? Okay, notice t is measured in hours. So all we have to do is plug 1 in for t. So after the first hour, t equals 1. So you're going to get y equals 100 e to the negative 0.6 times 1. My calculator was acting up earlier today. Hopefully it'll get happy. I had a dream that my computer died on me last night. The good news about that is that my dreams are never accurate. So I've learned not to have any, I think they reflect my fears more than my realities. 100 e to the negative 0.6. And so that's 54.88 grams after 1 hour. So this is actually an example of exponential decay. And the reason it's exponential decay is because we started with 100 grams and we ended up with 54.8. And the fact, I kind of knew it was going to be decay because the rate of change was negative, because of that negative 0.6. Now, what you might notice is that negative 0.6 ended up where in our equation? It ended up in the exponent. And that, it doesn't matter what the number is right here. If in the book he actually puts a k here, and he goes through this same integration and he discovers this formula is plus or minus e to the c, e to the kt. And then in general he says this e to the c, since it's kind of messy looking, he just calls that a. It's your initial condition. It's whatever was given in the problem, you know, when t equals 0, they give it to you. So that gets us to this idea of the law of exponential change, which is that y equals y naught e to the kt. Y naught is your initial value, or your amount at time 0. And it turns out that this type of growth is used all over the place in science and in finance, continuously at compounded interest. This is the function that's used for continuously compounded interest, and the K there is the interest rate. And then we'll look at some examples here that are application problems. Okay? So, and then, you know, I always encourage you to read in your textbook if you want more examples. Okay, it says, one model for the way diseases die out when properly treated assumes that the rate, dy dt, at which the number of infected people changes is proportional to the number y. So again, it's this idea that where y is the amount that's had the disease to begin with. So it says, the number of people cured is proportional to the number that have the disease. Suppose that in the course of any given year, the number of cases of a disease is reduced by 25%. If there are 10,000 cases today, how long will it take to reduce the number of cases to 1,000? Okay, so, oops, I hit the wrong button. I'm going to take these lines off because it's kind of irritating. So let me get you some space here. Okay. All right, so on this one, what we know is there are 10,000, it says, suppose the number of cases of disease is reduced by that in the course of any given year, the number of cases of the disease is reduced by 25%. So we start with 10,000 cases. How long will it take to reduce the number of cases to 1,000? Well, okay, we have this equation, y equals y naught e to the kt. And we don't know the rate, we don't know k, but we have some information that can help us figure out what k is. We know that at the end of a year, you have a reduction by 25%. So your initial amount that you started with is 10,000. So after 1 year, how many cases do you have? You will have, just give me a thought.
7,500.
Yes, 25% less, which is 7,500.
7,000. Yeah.
Yes, that's right, 7,500, right? Because you have 75% still have it, 25% don't. So 75% of 10,000 is, however you want to do it, 7,500. 7,500 cases, because it was reduced by 25%. So if I plug 7,500 in for y and 10,000 in for the initial amount, I don't know what k is, but I will be able to find it because this is true, these two numbers are true when t is equal to 1. Does that make sense? So now I only have one thing that I don't know. All right, so I will solve this for k. And let's see, that's 3/4, right? And let me just take a moment to tell you that you did not need to know, well, you do, to figure out what k is, you didn't need to know that there were 10,000 cases present because you knew it was reduced by 25%. You could have picked any number you wanted for the original, and you know on this side you would have 3/4 of it. So if you had put 1 here, you could have put 0.75 here. You see what I'm saying? So sometimes you can make up a number. If they tell you it's half what it was before, then make the beginning 100 and the other 50, and after you do that a few times, you'll see that you could have just put 1/2 equals e to the k. All right, now how do you solve this for k? Yeah, so you're going to do the ln, can I write that as 0.75, equals k times the ln of e. Of course, the ln of e is just 1, so that is your value for k. So k is equal to the ln of 0.75. So now you have a function that you can describe to figure out whenever, for any time. So now your function in general to model this scenario. I don't know how to spell that. Is y equals the initial amount, which was 10,000, e to the k, which is ln 0.75, and then t. So the question was, finally, how long until you reduce the number of cases to 1,000? So to find when you'll have 1,000 cases, you plug into y. So you're going to have 1,000 equals 10,000 e to the ln 0.75 t. And so then that, you can just solve this, right? So you can have 0.1 equals e to the ln 0.75 t. If you take the ln of both sides, you'll have ln 0.1 equals, this will be ln 0.75 t times the ln of e, which of course the ln of e is just 1. So you have ln 0.1 divided by the ln of 0.75 will be equal to t. And if you type that into your calculator, you get about 8 years. So t equals 8 years. Make sense? Kind of fun? All right. So now the next question is, how long will it take to eradicate the disease? That is, to reduce the number of diseases to less, or number of cases to less than 1. All right? So you'll put a 1 for how much you end up with. 10,000 was what you originally started with, e to the ln 0.75 t. So this will be 1/10,000th equals e to the ln 0.75 t. You take the ln of, let's see, tenths, hundredths, thousandths, 10,000ths, right? Equals ln 0.75 t, because the ln of e is just 1. So then you divide by the ln of 0.75, and you find that t is equal to ln of tenths, hundredths, thousandths, 10,000ths. You get 32 years. Bummer. So t is equal to 32 years. Be interesting to know, what do you guys know of a disease that has actually in essence been eradicated? I think polio is an example of a disease that has been eradicated, and they found the vaccine, and then they had a huge push to vaccinate kind of the world. And I have heard that although people have stopped getting the vaccine and it has kind of cropped up here and there, but I have heard that it did take years for it to be eradicated, though, but especially in the U.S. I mean, you don't hear of polio cases. Oh, well, I wonder if it was exponential. Okay. Now let's look at another example. It says suppose the amount of oil pumped from one of the canyon wells in Whittier, California, decreases at the continuous rate of 10% per year. When will the well's output fall to 1/5 of its present value? Okay. Well, it decreases at a continuous rate of 10% per year. Okay? So we need to figure out what what our rate is, our k. We're looking for our k. So we have this y equals y naught e to the kt. And this is the only information we have, is that it's 10% per year decreasing. But from that, you should be able to conclude if it's decreasing at a rate of 10% per year, then for each subsequent year, it's 90% of the, it's 90, after 1 year, it's 90% of the original amount. Does that make sense? So after 1 year, you have 90% of the original. So we can use that information. We can say 0.9 of the original, which is y naught, equals the original e to the k, and then this is after 1 year, so t is 1. So it doesn't matter what the original amount was, because you should see that the y naughts cancel. And so you know that after 1 year, it's 0.9 e to the k. And so your rate is ln 0.9, because you can take the ln, the k comes in front, and the ln of e is 1. And that's kind of like the one before. We had ln of 0.75 was our rate. Okay? So now it says, so now we have this equation, which is y equals y naught e to the ln 0.9 t. And it seems like we don't have enough information to answer the question, which is, when will the well's output fall to 1/5 of its present value? But what you want to end up with is 1/5 of what you started with, right? So if y naught is what you started with, 1/5 of y naught is what you end up with, right? So it doesn't matter what y naught is. You know that 1/5 of y naught is what you want to end up with. Kind of fun, right? Because then what happens is your y naughts cancel on either side. So it didn't matter. Because of the way this exponential properties work, it doesn't matter. You don't need to know how much you started with. And then 1/5 is 0.2. So we can say the ln of 0.2 is equal to, again, this is going to be, when you take the ln of this, ln 0.9 times t. So you just divide both sides by ln 0.9. and that's your T. So you have ln 0.2 divided by ln of 0.9. And then you get, he's been bad today. Maybe this was the dream. So I'm gonna have to have help from the audience. Anybody get it?
$15.28.
Yeah, 15.28 years. Okay, good. All right. So I was just kind of cutting and pasting things out of the textbook because, I just like to steal from him. And so I decided to steal this formula to calculate. I cut it out. I don't know why I said it again, except that when you have radioactive decay, you can put a big old negative there on the K because the rate is going to be decay. It's not always going to be negative, but when you're looking at radioactive decay, it is. Two thoughts I had, like if you have nothing to do one day and you're looking for something to do and you don't want to spend any more time on YouTube, Chernobyl, if you just Google Chernobyl, it's like the most fascinating story to read. Chernobyl is where they had a big nuclear explosion, a power plant in Russia that exploded in like 89, which you guys may not have even been born. Yeah, the event and the consequences of the event are huge on a population of people that we never hear about. But something like 50,000 people died within the first couple of years. And when it happened, of course, a bunch of people died. But then these workers, and this is so Russia, because Russia, they don't really care about, back then, the USSR, whatever, if someone told you to do it, you had to do it. And what they did was they just told people, you're going to Chernobyl and you're going to encase this power plant with metal. And so they had to go, they went and they encased the entire plant in this metal thing. And you can see photos of it. It's like this monolith. It's the scariest looking thing. And when you're looking at it, you know that every single worker, every single person that said, okay, I have to go to Chernobyl, every welder, and I have to weld this seam, and while I'm doing this, radioactive substance is going to get on my body and I will be dead within a year. I mean, it's just like just looking at it, you're looking at a tomb. It's really unique. So, interesting. So you should, I don't think that nuclear power is dangerous. What they did was dangerous, very dangerous, and you can read all about it and form your own opinions. But, that's what, it had an explosion and they had radiation poisoning. But the thing is, they ignored the engineers that were talking about the problem, and they only listened to the bureaucrats. And then there was a mistake, a huge mistake. But, and with tremendous consequences. But anyway, so if you're ever, Chernobyl is a fascinating thing to read about if you're ever just on the internet. And it deals with this idea of radioactive decay. The other thing that's interesting in this section, I don't know if, and this is probably me because the math isn't, as scary. This wasn't me when I was at your level of learning it. But this whole idea of the logarithm and its cool little properties and all of that is really interesting. And John Napier is the man who discovered the logarithm, or kind of created the logarithm. And he actually created it as a tool for calculating. Like the slide rule is based on the logarithm. And he spent 20 years of his life basically trying to come up with a calculator. But this function that he created to make the calculator has then just blossomed into all of these other applications. So it's kind of neat. So those are the two things that I think about in this section besides just the math. So if you're bored, look up Chernobyl. I don't know. But in Google, you can just, if you have an iPhone, you can just say Chernobyl and it'll come up. I don't know. I'll look for you. I don't know. TR, something. You could look at nuclear power plant explosions, and it's right there on the top. It's a big one. Okay. So example 4 says the decay equation for radon-222 gas is known to be as above. Okay, which is the thing I wrote you. Okay, that thing. With K equal to negative 0.18 with T in days. About how long will it take the radon in a sealed sample of air to fall to 90% of its original value? Okay, and so all you have to do is do, all right, Y equals Y naught e to the negative 0.18 T. And are you guys okay? Can I just put 0.9 equals e to the negative 0.18 T? Or, I could put a Y naught here and a Y naught here, and I see that they cancel, right? Okay. And then, so then I get that the ln of 0.9 is equal to negative 0.18 T times the ln of E. Of course, the ln of E is 1. So I get the ln of 0.9 is equal to negative 0.18, which is T, which will be T. And if you type that into your calculator, I need help from the audience. 0.585 days. Okay, and so the other thing about radioactive material is like its half-life, the half-life of, what is that they use? Like plutonium or whatever, I don't know. Whatever that thing is, its half-life is like 1,000,000 years. And so that thing will be radioactive forever, for as long as humans are on the earth. And so that's why it's so dangerous, like nuclear submarines and all that stuff is so dangerous. Okay. All right, let's look at example 5. The other application to exponential functions or dealing with exponential decay is carbon dating, which you may have heard of before. And it says, the decay of, so this is example 5, the decay of radioactive elements can sometimes be used to date events from the Earth's past. In living organisms, in a living organism, the ratio of radioactive carbon, which is carbon-14, to ordinary carbon stays, it was late, fairly constant during the lifetime of the organism, being approximately equal to the ratio in the organism's surroundings at the time. After the organism's death, however, no new carbon is ingested, and the proportion of carbon-14 in the organism's remains decreases as the carbon-14 decays. Scientists who do carbon-14 dating use a figure of 5,700 years for its half-life. Okay, all right, so that's some information there. Now it says, the charcoal from a tree killed in a volcanic eruption that formed the crater lake in Oregon contained 44.5% of the carbon-14 found in living matter. About how old is the crater lake? Okay, so we're going to use our formula, y equals y naught e to the kt. Now, we're going to have to get the k. And since we're dealing with carbon-14, we're going to first begin with this sentence right here. 5,700 years is its half-life, okay? And so that means that you will have half the amount that you started with after 5,700 years. So if you start with 100, you'll end up with 50 after 5,700 years, right? So in order to find k, we can use this equation and we can say that half of y naught is equal to y naught e to the k times 5,700. Everybody okay? And then the y naughts cancel, and then you have the ln, and I'm going to say 0.5, is equal to k times 5,700, and then that's the ln of e, which is just 1. And so when you divide both sides by 5,700, you get your K, which is your decay rate. And it turns out, in general, if you know the half-life, you can find the rate by doing ln 0.5 over whatever the half-life of your substance is. So does that make sense? I mean, you can kind of see how that would work out. If all I ever had to change was the 5700, like for some other product, it might be 200 years, and then it would just be ln 0.5 over 200. Or if you were asked for the doubling time, you could put a 2 right here. It would be ln 2 over, they can tweak the questions, but you can really kind of reason them out. Okay, so now we have a formula, which is y equals y naught e to the k, which is ln 0.5 over 5700. That's just some number, and then we have a t. Okay? So now it says the charcoal from a tree killed in the volcanic eruption that formed the Crater Lake contained 44.5% of the original. So you can put 0.445 in for y, and then leave out the y naught, or if you want, you can just say 0.445 of y naught is what happened, and we're looking for the when. So you see that the y naughts cancel. It doesn't matter how much we started with. Okay, and then we can take the ln of both sides. So we have ln 0.445 equals, this will be ln 0.5 over 5700 times t. Of course, the ln of e is 1, so we don't have to worry about that. And so then, why did you do that? Undo. Oh, my whole thing went whacked on me. Look at that. And I tried that, though. It didn't. See, maybe my dream was accurate. All right, I figured this out one time before. Technical difficulties. Please pause the video or fast forward the video while Mrs. Brooks figures out what she's going to do with this. Where was this, ln? What happened? Well, it looks like a mess, doesn't it? God. Psycho thing. Where's my delete? All right, I'm gonna write it real quickly again. Sorry. Okay. All right, so the half-life was equal to the original amount, e to the, we don't know how long, we don't know what k is, but we know it takes 5,700 years. So you see that your y naughts cancel, and ln of 1/2 is the same as ln 0.5. And the ln of this is just going to be k times 5,700. And so, because the ln of e is 1, and you divide by 5,700 to get your k. So then your general formula is y equals y naught, e to the k is ln 0.5 over 5,700 times your t. Now they want to know that contained, 44.5% of the original. So that's 0.445 of the original is equal to the original times e to the, this is a number, don't let it scare you, and then you've got a t. And so you see that your y naughts cancel. And when you take the ln of both sides, you're going to have the ln of 0.445 is equal to the ln of 0.5 over 5,700 times t, and the ln of e, of course, is just 1. So when you solve for t here, you're going to multiply by the reciprocal of that. So that's going to be 5,700 ln 0.445 over ln 0.5 is equal to t. Okay, and so did anyone type that in for me? Yeah, 6,650. They have 59. Does that seem okay or no?
I got 58.3.
Okay. 50. I guess they rounded up. Years. About. What they did is they actually rounded this ln 0.5 over 5,700. So I'll go with the 8. Pay attention to whatever the computer says. I mean, you must have. Did you use this in its whole form?
Yeah.
Yeah, they didn't.
Set it as X.
Yeah, they didn't do that. Okay, one more formula that kind of deals with this whole thing is Newton's law of cooling. One more application. Okay, and so here you go. It says, this is Newton's law of cooling. It needs a little break. H minus H sub s is equal to H sub 0 minus H sub s e to the negative kt. So H is the temperature at a given time, T. H naught is the temperature when it starts, and HS is the constant surrounding temperature. Okay? So those are our different little parts that go into our formula. All right? So let's see if we can use this information to help us answer example 6. It says, suppose that a cup of soup cooled from 90 degrees Celsius to 60 degrees after 10 minutes in a room whose temperature was 20 degrees. How much longer would it take the soup to cool to 35 degrees? All right. So, according to our formula, we have H is, in this case, what we want to end up with, minus H, the surrounding, equals H, the initial, minus H, the surrounding, e to the negative kt. Right? All right, now, here we know that we want it to end up to be 35 degrees. So this is going to be my H. How much longer is obviously our T, right? We're wondering about our T. So we're going to put 35 in for H. H surrounding is the temperature in the room, which was 20 degrees. So we're going to put 20 degrees in for H sub s. Now, it's a normally 90 degrees Celsius. So, and let's see, hold on. The soup cooled from 90 degrees Celsius to 60 degrees Celsius after 10 minutes in the room. But hold on, I'm sorry. Okay, so H naught is the original temperature, which was 90, minus H sub s, which is 20, and this is e to the negative kt. So we have 15 equals 70 e to the negative kt as of formula. I may not have, hold on a second. But the problem with that is that we don't know what K is, right? So let's see if we have some information to figure out what K is. They told us that it cooled from 90 degrees to 60 degrees after 10 minutes in a room with a temperature of 20 degrees. So we can put our original temperature, our temperature that we end up with, okay, so I'm sorry, need to find, okay, all right, so we ended up with 60 degrees after 10 minutes. So I'm going to put that in for H. So I'm going to use this formula again, helping me to find, because I want to use the 10 for the T. I should have done this first. It's making it confusing. Okay, so it ended up to be 60 degrees in a surrounding temperature of 20 degrees. Its initial temperature was 90 degrees minus 20 degrees equals e to the negative, we don't know, k, but we do know this is 10, right? So that's good because then that's going to help us find okay. So 60 minus 20 is 40 equals 90 minus 20, which is 70, e to the negative k times 10. So this is 4/7 equals e to the negative k times 10. So we get the ln of 4/7 is equal to negative k times 10. And so that means that k is equal to negative ln 4/7 divided by 10. All right, and so you will go in here and figure out what that number is, or you can just leave it like that. And that is the value that you are going to plug in for this equation and solve for t. So 15 equals 70 e. The negatives are going to cancel there, so that's going to be ln 4/7 divided by 10 times t. And you should get first, to solve this, you need to divide both sides by 70. So you get 15, I wish I had my calculator was working, equals ln 4/7 divided by 10 t. Ln, the ln of this. So the ln of 1570 equals the ln of this times t, because the ln of e is 1. And then you have 10 over the ln of 4/7 times the ln of 1570 equals t. Can you try it? I hope it works.
Did you
Yeah.
forget the negative? The negative is...
Is your answer negative? I'm feeling like since I had the negative here and then it was negative again here, I feel like it should be positive.
Oh, okay. I see.
But I am feeling nervous about that, so I'm hoping somebody would type this bad boy in. Okay, that's right. Are you okay with the negative thing?
Yes.
Yeah. Okay. All right, and so if you type this into your calculator, you get t equals 27.5 minutes. But the question is how much longer? And so you've already gone 10 minutes, so it will be 17.5 minutes. Longer. Does that make sense? Okay. And then to answer the second part, it says, instead of being left to stand in the room, the cup of 90-degree soup is put in a freezer whose temp is negative 15 degrees. How long will it take the soup to cool from 90 to 35 degrees? Okay, well, on this one, we can still use, we have our initial, our H naught is still 90. We want to end up with 35 degrees, but our surrounding temperature is negative 15 degrees. So H minus HS equals H. Okay, so H minus HS equals H naught minus HS. And then times e to the negative KT. Okay, and so in this case, you're going to have, you still want to end up with 35 degrees. So you're going to have a 35 here, but your surrounding temperature is negative 15. So that's actually going to be 35 plus 15. Your initial temperature is the 90. Your surrounding temperature is still negative 15. And your K stays the same as before. So that was that ln 4/7 over 10 with a T. And it's positive because it's negative, but then your K was negative, so it becomes positive. Okay, so 35 and 15 is 50 equals 90 minus negative, so that's 105. E to the ln 4/7 divided by 10 onto T. So divide both sides by 105. And then take the natural log. And the ln and E, those will cancel, so you have ln 4/7 divided by 10 times T. So you should have 10 ln 50 over 105 divided by the ln of 4/7 is equal to your T, right? How did that go? 13.26. Are you getting that to type in okay on your calculator, Brandon? I wish my calculator's not working. A good idea is to store the value so you don't have so many parentheses. Okay, so that's it. I will see you guys in lesson 7.3, I think. Is that all? Yeah, that's it.